Is a presentation on carbon-oxygen bond forming using reductive elimination, specifically in platinum complexes. The overall reaction can be split into two main parts. The first part is an oxidative addition, and the second part is a reductive elimination. The second part is where that carbon-oxygen bond actually forms. All of these revolve around a platinum complex. In the oxidative addition, the main things that we can see happen is an iodobenzene diacetate molecule reacts with the platinum complex. In turn, the complex loses dimethyl sulfide and gains two OAC ligands. During this process, the platinum center's oxidation state also increases. In the reductive elimination, platinum's bond with Me and OAC breaks. The Me and OAC then bonds to form a methyl acetate separately, and the oxidation state of the platinum decreases back down to its starting state. When looking at the oxidation states of the platinum center, you can see that in the original complex, platinum has an oxidation number of 2+. After the oxidative addition, the platinum is oxidized to a +4 state, as it loses 2 of its electrons when it bonds with the 2 new ligands. After the reductive elimination, the platinum gains back its 2 lost electrons and returns to its +2 state. Looking at the 2 ligands that it loses at the end, we can see that they also, throughout the whole of the 2 reactions, have an oxidation state of -1 until they bond together to form MEOAC, which has an oxidation state of 0. The oxidative addition reaction mechanism looks like this. The first step is that platinum attacks iodine to form a bond. An OAC group then leaves to form a reaction intermediate. Iodobenzene leaves during these 2 intermediate steps, and an OAC ligand is added back onto the molecule. The final step is dimethyl sulfide being substituted for water. This is because it is highly unstable in air and will just react with any moisture in the air. The reaction mechanism for reductive elimination is much shorter, as the OAC ligands are trans from one another. It means that an OAC is always going to be adjacent to the methyl group due to the octahedral shape. The platinum then gets its 2 electrons back and when it's reduced, and the methyl and OAC will bond together to make methyl acetate, which, as you can see, that between the oxygen bond and the methyl group is the CO bond that we have created. The shapes of these platinum complexes change throughout both reactions. In the beginning, platinum will have, as it is a D8 metal with a +2 oxidation state, and it is currently in a 4-coordinate complex, it will form a square planar shape. This is because platinum has bigger p orbitals than some metal centers that form tetrahedral complexes, so a square planar shape actually has lower energy. Then, after reacting once, platinum will have a +4 oxidation state and will form an octahedral shape, like most other 6-coordinate complexes do. As its oxidation state goes back down to 2 and its coordination number goes back down to 4, it will, to fit the pattern, go back down to a square planar shape yet again. Finally, there were different analytical methods used to study the structure of the different platinum complexes. For example, the octahedral structure that was presumed to be present in the second complex that was looked at was determined by having crystals be grown via diffusion of hexane into a solution of CHCl2 and this particular platinum complex. It was found that the acetyl groups were in fixed trans positions on either side of the metal, which was expected, and then you could also look at the bond lengths. They were examined and found to be comparable to other trans ligands that were in similar shapes, so other platinum carbon, platinum oxygen ligands bond lengths, and then other carbon oxygen bonds in acetyl groups. Finally, peaks were matched up on the mass spec, and at 509 there was an expected peak that corresponds to the weight of this molecule. Thank you.